Hello and hi everyone. My name is Amrish Analaki Umapati and we are from Group 6 in for PSDA Section 4. And today we are going to do our presentation for our Project 2. So first of all, in this slide, we can see that we can see our objectives. So our main goal is to investigate how basic demographic traits and daily lifestyle habits act as a meaningful predictors of an individual's BMI, body mass index, using data-driven insights. The core problem we noticed in existing literature is that standard health metrics often treat BMI as a flat or a universal number, and they ignore how fundamental background baselines such as biological gender, age, and also age, like naturally will create completely different metabolic starting points for different people. Therefore, the ultimate goal of our project is to uncover these structural weight distribution patterns. By doing this, we can provide clear practical insights that can be used for personalized preventative management. Okay, moving onto our data set and how we prepared our workspace. For this study, we are utilizing a secondary data source retrieved from Kaggle, containing a massive sample populations of 50,000 unique records. This gives our model an incredible amount of statistical power. Out of the variables provided in the source file, our team isolated five specific target variables to align with our research boundaries. Our continuous dependent variable are body mass index (BMI), alongside with age, gender, physical activity level, and also categorically weight categories. So yeah, before running our main test, we performed critical data pre-processing inside our R Studio because we have to use R Studio in this project. We audited the entire data frame across all 50,000 rows to ensure that there were no missing values or blank entries that could break our functions. We also verified that our continuous boundaries for age and BMI fell within realistic logical adult ranges. And we converted our text columns into structured statistically factors so our studio could properly run our comparative groups. Now, let's dive into our first inferential test of our report, the independent two sample t-test. We set out to answer a fundamental question: is there a statistically significant difference in the true mean BMI between males and females in this population? As you can see on the left, we establish our mathematical framework. Our null hypothesis, H null, states that the mean BMI of females equals to the mean BMI of males. Our alternative hypothesis, H1, claims that they are not equal because the true population variances are unknown and the sizes vary slightly. We ran a t-test, a two-sample t-test under a strict 95% confidence level, meaning our alpha significance line is set at 0.05. You can also see our structural formula. We formally subtract 0 in the numerator to represent our null hypothesis condition. We chose this T formula is chosen because our variances are also assumed to not to be equal. So that's why we chose this T formula. When we executed this code, this script in our studio, the software generated some very extreme results. Our calculated t-score is a massive negative 62.392. Because our sample size is so large, our degree of freedom is 49,909. So if we check a traditional statistically t-table, the most like the bottom most row it's for large, and if for a two-tailed test at 0.05 alpha, our critical boundary value is plus minus 1.960. So our final decision is to reject the null hypothesis because our calculated t-score of modulus negative 62.392 sits way past our critical value, which is 1.960. And our observed p-value is also that is printed by our studio is less than 2.2 times 10 to the power of negative 16. In a practical context, this highly significant result proves that biological men maintain a visibly higher baseline average BMI of 24.09 compared to the woman at 22.86. For our group report, this structural variation is critical because it alerts our team that genders also must be treated as an essential control variable before we can accurately interpret the lifestyle and age regression models in our upcoming chapters. That is all for my presentation. Thank you.
Hi, my name is Shaz, and I'll be presenting the correlation analysis and regression analysis section of our project. For the correlation analysis, we examine the relationship between two numerical variables, age as our independent variable and BMI, or known as body mass index, as our dependent variable, using the Pearson correlation method at a significance level of 0.05. Our null hypothesis states that there is no significant linear correlation between age and BMI, while our alternative hypothesis states that a a significant linear correlation does exist. After running the Pearson correlation based on all 15,000 observations, we obtain a correlation coefficient of R equals to 0.3759, a t-statistic of 90.692, and a p-value of less than 2.2 times 10 to the power of negative 16. The 95% confidence interval was between 0.3683 and 0.3834, as shown in the scatter plot. Even though the data points are widely spread, the red variation line trends upwards from left to right, which visually confirms the positive direction of the correlation. Since the p-value is far below our significance level of 0.05, we reject the null hypothesis. The R-value of 0.3759 indicates a weak positive linear relationship between age and BMI, meaning that as a person gets older, their BMI tends to gradually increase. However, since R is not close to 1, we acknowledge that age alone does not fully account for BMI variation. Right, moving on to the regression analysis, we use the same variables, and which is age as the independent variable and BMI as the dependent variable. The objective here is to build a simple linear regression model to determine whether age can significantly predict BMI. Our null hypothesis states that there is no linear relationship between age and BMI, meaning the slope equals zero. Our alternative hypothesis states that a significant linear relationship does exist. After fitting the regression model on all 50,000 observations, we obtain the estimated regression equation. BMI equals 21.1966 plus 0.047 times age. This means that for every 1 year increase in age, BMI is estimated to increase by 0.047 kilogram per meter squared. Looking at the variation, the SSR is 36,687.1, SSE is 223,013.3, and SST is 259,700.4. From this, the R squared value is calculated as 0.1413, meaning that approximately 14.13% of the total variation in BMI is explained by age alone. The F statistic is 8,225 with a p-value of less than 2.2 times 10 to the negative 16, which is well below 0.05. Therefore, we reject the null hypothesis. There is sufficient evidence that age has an statistically significant linear relationship with BMI. However, since R squared is only 14.13%, H alone is not a strong standalone predictor. Other factors such as diet, physical activity, and genetics likely contribute more significantly to a person's BMI. That concludes my part. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Adam Baharudin. So my part, I will explain about chi-square test. Okay, for the chi-square test, the objective of this analysis is to determine whether there is a significant association between activity level and weight category. For this test, two categorical variables were selected from the dataset. The first variable is activity level, which consists of lightly active, moderately active, sedentary, and very active categories. The second variable is weight category, which consists of underweight, normal, overweight, and obese categories. Okay, for the hypothesis for this test are H0 activity level is independent of weight category. H1 activity level is dependent of weight category. A contingency table was generated by RStudio, followed by the chi-square test of independence. The result show the result from RStudio show a chi-square statistic of 139.8542 with 9 degrees of freedom. The critical value at a significant level of 0.05 was 16.919. The p-value obtained was 1.105662 power multiplied by 10 power or negative 25. Since the chi-square is greater than critical value, and the p-value is less than 0.05, the null hypothesis is rejected. So for the conclusion, there is sufficient evidence to conclude that activity level and weight category are significantly associated. These findings suggest that different levels of physical activity are related to different weight categories. Individuals with different activity levels tend to have different BMI related weight classification. Okay, that's all from me. Thank you. Assalamualaikum warahmatullahi wabarakatuh. So I will continue for conclusion part. So for the conclusion, descriptive statistics summarize the data set and provided an overview of the characteristic and distribution of the variable. Hypothesis testing determined whether there were statistically significant difference between the selected group. Correlation analysis measure the strength and direction of the relationship between continuous variable and BMI. Regression analysis identified the physical health indicator that can be used to predict BMI and evaluated their predictive relationship. For the chi-square test of independence show a significant association between activity level and weight category. Overall, the findings indicate that physical health indicators are useful in explaining and predicting BMI, supporting the objective of the study. Thank you.